we left off last time talking about 3 flattenability, and we're going to characterize it. So my plan for today is to characterize 3 flattenability, talk a bit about single interval frameworks, and then if you have any other questions, we can discuss that then at the end of the class. Okay, so where we left, we made a result a lot earlier saying that a graph is a partial 3 tree if and only if it doesn't have one of these forbidden minors. Okay, so K5, K222, or the octahedron, V8, or C5 cross C2.
Hey, Sean.
Yes?
Can you remind us what a partial 3 tree is?
Oh, okay, so a 3 tree is something you get by just gluing K4 simplexes together at faces, at triangle faces, and you just keep doing that operation. And then a partial 3 tree is just a subgraph of that. Does that make sense? It's a bit of a quick definition, I guess.
Yep, that was good. Thanks.
Okay, so basically, so with the previous cases of partial 1 trees is the same as being 1 flattenable, and partial 2 trees was the same as being 2 flattenable. But it's actually, so partial 3 trees is not the same as being 3 flattenable. Okay, and we're going to discuss that. So what's going to be our method of characterizing 3 flattenability? Well, first thing we're going to see is actually some of the above are actually 3 flattenable. And this is what I'm saying about partial 3 trees and 3 flattenability are not the same thing. Partial 3 tree, being a partial 3 tree is a strictly weaker condition. Okay, so our method for characterizing 3 flattenability. The first step is to prove that the minimal forbidden minors for 3 flattenability are some combination of the above. This will make things easier because it could be that maybe these two are, well, it's going to turn out that these two aren't 3 flattenable. We already know this one isn't. And these two are 3 flattenable. But it could be that maybe there's some other minor that we're somehow missing. So we need to prove that the minimal forbidden minors have to be some combination of these 4. And then we're just going to determine which of the 4 it is. That's the method we're going to use to prove it.
Sean?
Yep.
What does some combination of a graph mean?
Some combination of the 4 graphs. So not just some combination of a graph.
Or a union or
subset,
a glue?
yes. Yeah.
Subset.
So we're going to say that the forbidden minors is some subset of these. It's going to turn out it's just going to be these 2. But we're just going to prove that, yeah, it's some subset of these 4 are the forbidden minors. Because it could be, yeah, it could be these 2, and then there's some third forbidden minor, which is somehow bigger than these 2 and something like this. It could be something a bit funny like this. So, well, yeah, we're just going to prove that's not the case. And then we're going to determine which ones are 3 flattenable and which ones aren't. And that will give us the result. So that's the method. Okay. We've got a few cases to cover. So the first one is going to be low connectivity cases. So this will allow us to reduce the problem to 3 connected graphs only later on, which is going to be a lot easier. So when I mean low connectivity here, I'm going to mean, well, I guess disconnected is easy to do. You can always assume these graphs are connected, because if they're disconnected, you can just do one or the other component. 1 connected and 2 connected. They're the 2, not 3 connected and not 2 connected, but connected, I guess. Well, I'll explain in a second. So, okay, we've got here some graphs. We can assume they're all connected, and they're all joined together at 2 vertices, okay? But even more than that, they're all joined together at some edge xy. So each graph GI contains the edge xy, and then we've just glued them all together at the edge xy. Okay, this is going to give us our graph G, and we can also talk about G dash. So G is just we glue them all together at the edge. G dash is we glue them all together at the edge, and then we just take away the edge. Okay. What we're going to have is that the flattenability of all 3 of these graphs is exactly the same. Now, this is going to help us reduce to the problem of 3 connected graphs. Because if we have 2 graphs, if we have a graph that's got a one separating set, it's kind of easy to see that we can just deal with, we can separate it out into 2 graphs and then just deal with both halves. So we're doing the same with if you've got a 2 cut, that's a clique. If you've got something like this, we're going to be able to separate it out. Okay, and this is kind of the idea. What we're going to say is that, what we're going to prove later on is that, okay, if the graph is not 3 connected, but it is 2 connected, you would look at the separating set and realize, okay, I can actually just decompose this into 2 other graphs and then just repeat the problem later on. Right. So first thing, if G is deflattenable, then so too is G dash. That's fairly obvious. G just contains G dash. Okay. What else? If G is deflattenable, then it's immediate that these are all deflattenable as well. But we can also actually say that if G dash contains G1 to Gn as minors, then G dash does contain G1 to Gn as minors. So if G dash is deflattenable, then so are G1 to Gn. Now, the way to see this is each of these graphs GI is connected, and a connected graph can always just by edge contractions, can just be contracted to a single edge. Okay? So what we can do is, if we want to look at the graph G1, we contract G2 all the way up to Gn to a single edge. And then what we've got left is we've contracted from G dash to G1. So G1 is always a minor, and similarly, so is the same for G1, G2 up to Gn. Okay? So the only direction that we have left to prove is that if we have a load of graphs that are deflattenable, so these G1s to whatever, and we glue them all together at an edge, the graph G is going to be, from this gluing, is going to be deflattenable. Okay, so if we assume they're all deflattenable and we choose a realization of G, okay? What we're going to now basically say is that, so we have this realization P of G. This is going to be in however many dimensions you want. What we're going to basically say is we can decompose P into these PIs. So the PI is just a restriction of P to the vertex set of GI, the set VI. So we can decompose it into these different components. Each one of these components is flattenable. Okay. And then we can just basically say, okay, we can kind of glue them together in a sensible way. So to be slightly more specific, we've chosen our realization P of G, and we define PI to be the restriction of P to the vertex set of GI to VI. As each of these GIs is deflattenable, there exists a d-dimensional realization QI of GI. Okay, that's just from definition. By applying translations and rotations, what we notice is that we can always assume that the x coordinate of the Q thing is at the origin, and the y the x vertex of the Q is at the origin, and the y coordinate is on the x-axis. So maybe x and y weren't the best choice of letters, but yeah. So we've just translated it, put one vertex here, and then rotated it around until it touches the x-axis. But we already know that the length of the distance from QIX to QIY has to be the same for every single y, because they all came from this placement P. And P has a set length, so that means all the PIs have the same length between the 2 vertices. So I've got this CI here. Well, we know that this CI has to be constant. Okay? And now we just say, okay, well, we know where each QIX is and where each QIY is, so we can just glue the QIs together to form this new realization Q. Q is going to be d-dimensional, so then it follows that we've flattened out GP into GQ, and we're done. Okay? And as you notice, this works in any dimension. We can kind of say something similar with what's it called? If we have any clique. So what I've got here, basically, if we have a graph which is deflattenable, and instead of it being xy that they all contain, it was xyz, so it was like a triangle. As long as it contains all the edges in each one of these GIs, then you can make a similar statement about G and GI. And then similarly, you can make a similar statement with G dash. So this result can be extended to higher cliques, but we only need it for edges. So that's the reason for just doing it this way. But yeah, that's a homework problem. If you want to do it, you can extend this.
John?
Yep.
But then there'd be restrictions on the D related to how big the clique is?
Yes, yeah, that's true, yeah. I guess it would be, would it cause problems? I guess it would just be trivially true in some ways, maybe. Let me think. Oh no, I guess this G dash would cause problems. Yeah. So yeah, there's a restriction on the size of the clique. Yeah. You have to make sure the clique's not too big.
So D flattenable, you could work with anything up to a D clique.
Yes.
But bigger than that, you'd have a problem with this.
Yeah, bigger than that, you're going to have nothing's flattenable. So it's going to cause a problem.
Sean, I was going to say, if all of the GI just have a common subgraph, and you know that all the GI are flattenable, then as long as you realize the common subgraph in the same way, then it seems like it should work.
It does not, because you could have the common subgraph is maybe like a tree, and it could be one realization has maybe it's just a path of length 3. So one of them it's like this, and another one it's like this. Well, then we can't do the gluing operation that we did. It is required, the subgraph is required to be a clique.
Okay.
It might be true, but the proof that I've given will not follow at all.
Right.
In fact, I don't think it's always true. I think you can construct examples where it breaks.
Okay.
So this actually ties into, if I can find it, this thing here. So we got a graph here and a graph here. You can see the two different graphs. They share a subgraph, which is just these two vertices. But what I've took is a 2 flattenable graph and glued it together with a 2 flattenable graph, and I've got something that's not 2 flattenable.
Right. Yeah, okay.
Wait, why isn't that example, Sean, why isn't that example why isn't that G prime for?
Because the two graphs, G1 and G2, one of them's K4, which is not 2 flattenable.
Ah.
So it does tie into this result, basically.
Right.
The result says they're, yeah. Oh, actually, maybe I should be a bit more specific. Yeah, well, okay.
So, yeah, this,
maybe
the proof uses G deflattenable and
yeah,
like 1 and 3 being equivalent.
I think I should remove 2. So if we cross out 2, I think you're right. I think this is not correct. Is this
actually, yeah, for the same example, right? Because if you add the edge, you've got G. If you subtract, you've got G dash.
Yeah, so I think remove 2. Yeah. Because I don't think 2's even, So where does it go wrong? No, it's still fine. It's still fine. Because G dash is still not so G dash is still not 2 flattenable in that case. Yeah, so no, it's still fine. 1, 2, and 3 are still equivalent. There's no issue with that. Because the graph that we've got is the K4 minus an edge with it's basically you've took K4 and you've done you've divided up the edge. You've subdivided the edge. So that's still going to be not 2 flattenable. So it doesn't contradict this at all. The statement is still fine. Yeah, sorry, I got confused then.
So, okay, so I understand from the proof why 1 implies 2 and why 1 implies 3. And I understand from the proof why 3 implies 1. Okay. But why does 2 imply 1?
So Alex has put the proof did 1 implies 3. It did not. It did 2 implies 3 here. So this sentence here.
G prime contains these guys as minors.
So I think this is the part that doesn't extend to higher cliques. What I'm saying is if you take one of the GIs and you contract it, you can contract that to an edge. So that fills in the edge. So you take G1 and you take G2 and you contract G2 because they're joined at a single thing and there's no edge here. You can contract that to a single edge and then you've got G1 in the graph.
Right. So 2 implies 3.
Yes.
That's true.
And then that's fine.
And then 3 implies 1 is the argument that you're making. So everything loops around. Okay. Yeah.
So this argument, this argument will, for higher cliques, will fail if you include 2, I guess. Because my argument was that if you have a missing edge, you can always contract the rest of the graph to a missing edge. But if you have a clique with no edges, you could contract the graph and only get 1 edge or something like this. So that part will fail. But yeah, you can still do this for higher cliques and say 1 is equivalent to 2. That's fine. So the bit that's a bit different is the G dash. And there's something in the chat as well.
I think
Yes.
I was just explaining the applications. That's right.
Okay. So from this, we basically said that the 1 connected case and the 2 connected case we can ignore. Because if we have a 2 cut, if we have a 1 cut, then it's fairly easy to see that we can just separate this out into 2 graphs and just deal with the flattenability in either of the graphs. And what this result here says is that if we have a graph that's 2 connected but not 3 connected, we can go to the 2 cut and either it's going to have an edge, in which case we've got G, or it's not going to have an edge and we have G dash. But in either case, this is equivalent to just the components when we separate them out, add in the edges as we need to. It's equivalent to them being deflattenable. So basically this says we can always just reduce to the 3 connected case. This is the only one we care about. Okay. I think I do this as a bit of a black box. I'll just double check. Yeah. So we have a lemma here. And it says basically if my graph is either V8 or C5 cross C2, and I pick any 2 vertices that are non-adjacent in the graph, if I add the edge, then, it should say contain as a minor. So if I add an extra edge in, I'll always contain K5 or K222. So to give a quick look on this, if I take this graph and I add an edge here, basically I can contract the rest of these edges into 1 single vertex, and then I'll have K5. So I'll show that with a pen. So if I draw a line, sweet, I don't know why that's that color. If I draw an edge in between here, then I've got a K4. So I've just added some edge. And then I can contract, if I contract this edge, this edge, this edge, this edge, and this edge, or all of these edges. So if I contract all of them to be 1 vertex, what I now notice is that this edge, this vertex is connected to here, this vertex is connected to here, and this vertex is connected to here. So when I contract it, I've got a K5. And basically, this lemma is why I didn't go into it, is just you're checking all possible cases. Because of the transitivity of the graphs, it makes things a hell of a lot easier to just do. But in the paper, they just check all the cases. There's not many to check, and they just check them. So I didn't want to go into too much detail on this. But yeah. So the lemma says, if I have a V8 or a C5 cross C2, and I add an edge, then it's going to contain either K5 or K222 as a minor. So this should said as a minor. Okay. Right. We're going to make an extra definition here. You might have seen this in terms of rigidity, and this is kind of close in some ways. So what this is saying is we're looking at a special type of edge contraction. So if you have a graph G and you have a graph H that's obtained from G by contracting an edge where both vertices have degree at least 3. So I'll draw that out. So we have one vertex here, one vertex here. We know they both have degree at least 3, so there has to be 2 extra edges here and 2 extra edges here. When we contract it, we're going to get something like this. Okay, maybe we have some extra edges over here, some extra edges over here. Okay, the operation that goes back, so that takes us from H to G, we call a vertex split, because we took a vertex and we split it. Now, if they don't both have degree 3, so say we have something like this, and then that's doing something over here. The operation we get when we contract this edge is going to be like this. And then we're going to get this other vertex over here with the 3 edges sticking out. So we've gone from here to here. Now, this is not called a vertex split, basically. And the reason is, if you look at it, going from here to here, all you have to do is subdivide an edge. Well, from here to here, you can't. That's not how you got them. That's not how you went from H to G. Does that make sense? So in the rigidity literature, they have special types of vertex splits, where I would split the vertex, but I would have maybe some edges go across and stuff like this, and there's certain rules on it. But here we're just doing a very basic thing. If I can go from here to here, like I said, contracting an edge where the endpoints both have degree at least 3. Going back again, we call that the vertex split. And this is kind of like we call this a subdivision of an edge, but we won't require it. Okay. Why have we done it this way? Well, there's this really nice theorem from Seymour in the 80s. So it basically says if we have a graph that's 3 connected and it contains a 3 connected minor that is not the wheel graph. So that's our assumption. So H is 3 connected, but it is not the wheel graph. Then we can always obtain G from H by a series of either just adding edges or these vertex splits. Okay? It's a bit of a strange theorem, but it's going to be very useful for us. What to consider about this is basically that the graphs we're dealing with, K5, K222, V8, and C5 cross C2, all of them are 3 connected. None of them have any 2 separating sets. So they're all 3 connected. So we can always do these sort of edge additions and vertex splits to get from the minor to something else. This is what we're doing here. Okay. Right. So now we've got this lemma, which is what we're going to be using. So G is going to be a 3 connected graph, and we're going to say that it doesn't contain K5 or K22 as a minor. If it does have a minor that's V8 or C5 cross C2, then the graph is C5 or V8 or C5 cross C2. Okay? And you can kind of see why we're going to need this, because what we're going to say is, what we're going to prove later is that these 2 graphs are not 3 flattenable. So, and we know that if we have something that's a partial 3 tree, so if we have a graph that doesn't contain this, 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 or this, then we know for a fact that it's 3 flattenable. So the only case we have left to check is if we have a graph that doesn't contain this or this, but it does contain one of these two. And what we're going to say is that, okay, if we have this, then the graph is V8 or C5 cross C2. And then by proving that those two graphs are 3 flattenable, we've finished the proof. And that will finish the proof. Okay. So by Seymour's theorem, G can be formed from H by a sequence like so. So we start at G0, we go to G1, G2, so on and so forth, all the way up to G. And the way we do it is every time we're just throwing in an edge or applying a vertex split. That's all we're doing every time. Obviously, if n is equal to 0, then G is just equal to H, and we're done. That's what we have over here. If n is greater than or equal to 1, then I claim, and I'm using it as a bit of a black box, then G1 will contain H plus E for some edge not equal to E as a minor. So obviously, if G1 is obtained from G0 by adding an edge, this is clearly true. But I'm also saying that if G1 is obtained from G0 by a vertex split, then it's still true. Basically, the way to check that. Oh, sorry. Yeah, Will.
Don't you just contract the vertex split edge?
No, because if we contract it, we will just get H. We won't get H plus E. So we got some extra.
Ah, I see. Okay.
That's the important thing. Basically, to prove this, all you do is you check cases. Because the graphs of V8 and C5 cross C2 are vertex transitive, there's literally a very small finite number of cases you need to check. And I didn't want to go into it because it's a bit tedious, but all you do is you check what happens whenever you do a vertex split. Because these are very, if we do an edge subdivision, it's not true, but if it's always a vertex split, we can show it's actually always true. And it is just, yeah, you draw out the graphs, you look at them, it's always true. By our previous lemma, it follows that G contains C5 or C222 as a minor, which is a contradiction. So that means that the only case that can work is n is equal to 0. And the proof is done. Okay, so we've only got we've only got 4 things left to do, or 3 things left to do. We have to show that we have to determine which of the 4 minors, forbidden minors, are actually forbidden minors, I guess. The 4 possible candidates. So the first one is this one, C22 is not 3 flattenable. That's the first thing we prove. Okay, I'm not going to give too many in-depth proofs on this sort of thing. So it's just going to be kind of sketches of what's going on. Okay, so to prove this, we're going to pick an edge of our octahedron graph. And then the remaining 4 vertices can be basically grouped, as I said. So we picked any edge. Then the last 3 vertices, Z1, Z2, Z3, Z4, we're going to have that Z1, Z2, and Z3 are a clique. So they form a triangle. Z1 is only adjacent to X, and Z2 is only adjacent to Y. And then Z3 and 4 are adjacent to both. You can just check this on the graph. This is always true. Because of vertex transitivity, yeah, if you can show it for one graph, then it's always true. Okay. What you can now do is you can actually form a realization of K22 where Z1, Z2, and Z3 are collinear but distinct. Px and Py are the same point. And the set Px, Z2, Z3, and Z4 are in general position. Okay. Which is kind of a bit of a thing. So I'll show you kind of in picture form. So we've got Z1, Z2, Z3. 1, 2, 3, a collinear. We're going to have a point up here, which is going to be X and Y. Okay. And we're going to have another point here, I guess, in a different plane for Z4, basically. So you can picture these lot being in some plane and X and Y being in the third dimension. Okay. What we're going to have is basically that there's going to be a finite amount of, so this thing has to lie in 3 dimensions, like I said, just from how I've done it, because 3 of a collinear, we have another one that defines a plane, and then the fourth one, the fourth and the fifth, the X and Y are the same thing. So this thing has to be 3-dimensional. What we notice is that there are only finitely many realizations of this in 3 dimensions. Modular isometries are equivalent to this minus an edge P. And the reason is basically the edges that we have remaining kind of go like this. So the edges that we have to fill in. Like so. PX is joined to Z1, Z3, and Z4. And so this is just a 0 extension to add the X, a 3-dimensional 0 extension. And the Y is the same, but we join it instead of to 1 to 2. So what we've took is something like this kind of weird, it's not even a triangle. What we've taken is 3 collinear points that are all connected, so this is rigid, and added an extra vertex connected to the endpoint, so this is still rigid. And then by applying the 0 extension, we've got something that's still rigid. And then applying the same with Y, another 0 extension, we've got something that's still rigid. So in 3D, we don't even need the last edge, and the last edge will be between X and Y, but we don't actually require it. So we form something that's rigid, not infinitesimally rigid, it's just rigid in 3D. Yeah, Will, do you have a question?
Yeah, sorry, I don't understand why Z4 is connected to Z1 and Z3.
Z4, it just has to be just in how the graph looks, basically. I probably spelled it out quite quickly, but yeah. If you look at the octahedron graph, this has to happen. Yeah, I've skimmed it a bit.
Okay.
Yeah.
Okay. Yes, I'm okay with that.
Okay, so because this is rigid, we know that there's only going to be finitely many realizations in 3 dimensions that are equivalent to it. Okay. Now we have to go into 4 dimensions, and this is why I wanted to give a sketch of the proof and not really go into it too much. But basically, what we're going to notice is that the vertices Z1, Z3, and Z4, they act as a hinge in 4D for our vertex X. Because in 1 dimension, 1 point makes a hinge. In 2 dimensions, 2 points make a hinge. In 3 dimensions, 3 points make a hinge. Okay, so what we now do is we take our vertex, it's connected to these 3 other vertices, and we rotate it in 4 dimensions. So we're rotating PX out, okay? Now, I said that the distances in 3D, there's only, because there's only finitely many realizations in 3D of K222 minus XYP, there's only finitely many distances that we can possibly have between PX and PY in 3 dimensions. But in 4 dimensions, because we have a continuous flex, we have an infinite amount. So obviously, only finitely many of them can be realized. Most of them can't be realized. So our last step to create our unflattenable framework is we take our vertex X and we rotate it in the 4th dimension to some point which cannot be flattened, and then we add the bar between X and Y. And then this framework in 4D cannot be flattened at all, which is quite a nice way of doing it. Is there any questions on that? It's a bit strange. It's hard to think in 4D. So this is some of the problems. No. Okay, I will now move on then. In which case, okay.
So I have a question.
Oh, yeah.
Yeah, so the graph you drew is rigid, but not infinitesimal rigid, right?
It's not infinitesimally rigid, no.
So why is that?
Because you can just use the combinatorics. So K222 is minimally infinitesimally rigid. So if you remove an edge, any placement has to be infinitesimally flexible. That's it, basically. If you're infinitesimally, if a graph's infinitesimally flexible at a generic point, then all of it, every single placement is infinitesimally flexible. So that's why.
So, okay. So, okay, I see. Thank you. Yeah.
Okay. Right. So next is to prove V8 is flattenable. Now I'm not going to prove this because the proof is quite complicated. I'm just going to sketch out why it works because the idea is more interesting than the actual technicalities. So what we're going to do is we're going to take any framework V8P. So we took V8 and it's in some dimension. We choose two vertices X and Y. And what we're saying is they're at least 3 away from each other in the outer ring. So what this means is we took maybe this vertex and 1, 2, 3, this vertex. So this will be X and this will be Y. Okay? We take them so they're 3 away. What I now claim is that by moving X and Y away from each other until they can no longer be any further apart, we can find a equivalent framework V8Q. So all we've done is we've took our framework in however many dimensions, and I claim that we can always just stretch it out until those two are as far apart as possible. It's effectively what we've done. So if it's not flexible, then it's not a problem. If it is flexible, we just stretch it out as much as possible. Okay. So Connolly, when he does this, Connolly and Belk use the idea of there's a strut. You put some strut in between them, and you've just extended the strut as much as possible, so they're as far apart as they can possibly get. Okay. Since the distance between these two is maximal, then there's a result that Connolly has that proves that there is a non-equilibrium stress. Basically, the idea is kind of you've forced yourself into a bit of a weird position where because it's maximal, they can only go in, they can only get closer together in a way. It's basically the idea. I don't want to go into it too much, but yes, it's vaguely the idea. This paper is just Belk. Yeah, Will is correct. Yeah, sorry. This is just Belk, by the way. Sorry, it's not Connolly and Belk, it's Belk. Okay, so they get this stress off this thing. What's the point of the stress? Well, the stress can then be used to kind of gain insight into the geometry of the framework. So for instance, if you have a stress between, if you have a stress on a triangle and nowhere else, then you know that means, so if the stress is non-zero on the triangle and everywhere else it's 0, you know the triangle is degenerate, you know it's flattened out in a line. And this is basically the idea of what they do. They say, okay, well, we have this stress. This tells us all the information we can get, and it boils down to a few cases. So what we then do is we check all the cases. And in every single case, the framework can be flattened. Now, if V8Q can be flattened, then it means that the original framework that was equivalent, V8P, that can also be flattened into 3D. And that's the idea. So it's a bit of it's quite a nice way of dealing with it. We can also do a similar argument for C5 cross C2. So there's a similar method of basically you put a strut between two of them, you extend it out, you look at the stress you got, and then you boil it down into individual cases. But I'm not going to go into this because this roughly takes about 15 pages of working to prove. There is a lot of cases to check. This is kind of, to me, indicates why talking about 4 flattenability is very difficult, because even talking about 3 flattenability is very, very difficult. And it also kind of indicates why we want these minor free properties, because determining whether a graph is 3 flattenable without them is very difficult. Okay. With all this, you combine all this together, and we're going to be able to show the theorem. So a graph is going to be 3 flattenable if and only if it doesn't contain K5 or K22 as minors. So as K5 and K22 are not 3 flattenable, the only direction we need to do is the other direction. Okay, so we only need to show that if a graph does not contain them, then it is 3 flattenable. Okay, so take G to be a graph that doesn't contain them. By our previous results, we may as well assume that G is 3 connected. If it isn't 3 connected, we can always separate it out into subgraphs, and then we just check the flexibility, sorry, the flattenability of the individual subgraphs, maybe subgraphs plus an edge or something. We can just check the flattenability of them. And if they're all flattenable, then the original graph was flattenable. So that's all we need to do. This is why we have this. So we can just assume that G is 3 connected from the off. Well, if G is 3 connected, if G is 3 connected and it doesn't contain V8 or C5 cross C2, it's a partial 3 tree. But if it does contain V8 or C5 cross C2, then it is equal to V8 or C5 cross C2. So if it doesn't, we know it's a partial 3 tree, then it's 3 flattenable. If it does, is equal to V8 or equal to C5 cross C2, and we've just shown that those two are 3 flattenable, and therefore we're done. And that's the proof. Any questions on that? Okay. Right. I've got now some stuff on single interval frameworks, but I've only got 15 minutes left, so there might not be much point going into it too much. So yeah, in fact, I'll call it an end here. I'll call this the lecture. If you're interested, I've got some other stuff on SIP stuff, but otherwise, here is the references for everything I've covered, including some stuff I didn't. Yeah, and does anyone have any questions about any of that? And previous lectures as well included.
So if nobody else has a question, I just wanted to quickly go back to the G sub i's gluing them together idea. So I think I phrased what I was trying to say badly, but I think if you have, say, just G1 and G2, and their intersection is a connected graph, then I think the argument still works.
It does not.
It doesn't?
It does not. There are examples.
Huh. Okay.
Yeah. Yeah. It is unfortunately incorrect. So, I mean, you could take a graph where try to think. So we could do a graph where adding an extra edge causes a triangle, which then causes the graph to not be flattenable. Okay. So we got like 2 edges like this. And then we could glue a framework at those 3. And basically then there'd be a way of contracting it so we get a triangle. And then this would be not 3 flattenable maybe or something. There are other ways of doing it. I could probably cook up an example at some point, but.
So does GI contain the intersection in these?
Yeah, it's still a problem is the thing. It's still an issue.
Okay. Huh.
It's not just connectivity. It needs to be a clique. That's what's required, basically. You can kind of get away with it in 2D, basically.
Oh, I see.
But in anything bigger, it starts falling to pieces.
Okay.
Does anyone else have any questions? Okay. We've got an extra 10 minutes, I guess. If anyone has any questions about single interval frameworks, then I'm happy to answer some of them, but we didn't really cover the topic.
Just define what one is.
Okay, so I'll do the definition, but I won't go through the proofs. Okay, so what's a better way of describing it than all this? Okay, so we take a graph and we take an edge that's not in the graph. That gives us a pair G and F. And we say that it has the d-dimensional single interval property is if that no matter what framework you give me for G, if I look at the configurations, if I look at the distance between the endpoints of F, that will always, the distances between them will always make a interval, basically. So maybe it's how it flexes and it makes an interval, but maybe you could reflect it and put the point over somewhere else. It will still just make an interval in a way. Does that make sense in a way? It's kind of like any equivalent. If you look at all the equivalent frameworks to your framework, then and you take all the distances that F, all the possible lengths of F, and you put that together as a set, that set will be an interval. And this is the single interval property.
So in contrast to having like some kind of loop or some kind of tree, what would the contrasting thing be?
So contrasting thing would be you have something where, okay, actually I can give an example. So this would be something that doesn't have the two-dimensional SIP. So all I've took is K4, I've removed an edge. So the graph that I'm doing the single interval property with is the one that's in bold, and the line that I'm applying it to is the dashed line here. Now this doesn't have the single interval property because I can find a framework where I draw it literally like this, and the possible distances between this vertex and this vertex is either 0 or √2.
Right.
Because I can have it like this, or I can fold it over. So this doesn't have the single interval property.
So here, the configuration space is just 2 points, right?
Yes.
But what if the configurations, do you have an example where the configuration space is 1 point, one dimensional, but it's not a single interval? Is it a loop then? Like, should I be thinking of it as a circle?
No, not necessarily, because you can have stuff that's flexible with the single interval property, and you can have stuff that's flexible that doesn't. So, I mean, I could cheat and just put an edge here or something like this. This would still not have the single interval property, even though the configuration space will be a loop.
But now the configuration space would have two connected components. It would be a loop and then reflect over to another loop.
Yeah. So if the configuration space is just a single loop, then that framework will have the single interval property. But you've got to make sure that every framework has the single interval property, I guess. It's kind of the idea. But yeah, having a single loop is fine. That's, yeah.
So if the particular pair of non-adjacent vertices you care about are globally linked, does that count as having single interval property?
So this is a big question, because globally linked, a lot of it's to do with generic, and it gets a bit hazy. So I did look into generic single interval property at one point. The problem is basically nothing is really known about globally linked vertices. I think Tibor and Shinichi did some stuff, but they don't have any definite answers.
Tibor, Bill, and Zoltan Zabadka have a couple of papers on this.
But there's no 100% guaranteed characterization. You have to use like sufficient conditions to say that it's true, as far as I can tell.
Yeah, even in 2D, it's not an easy thing.
Exactly, yeah. So this is kind of where the problem comes up. The single interval property, because you can say that you're looking at every possible framework, it makes things a bit more tractable in some ways. But yeah, it's a difficult question. The characterization for, actually I need to get rid of this line, I think. Drawings. The characterization for the 2D version is this. So it basically says that a pair has the single interval property in 2D if and only if every maximal clique two-sum component of G plus F that contains F is two-flattenable. So a clique two-sum component is basically you look for a two-cut, which is a clique, and you separate the graph out, and you do that. And a maximal one is just as big as it possibly can be. And what we say is, we say this result here. Now, this is going to have the single interval property, this pair. So the graph is all the lines that aren't dashed, and the dashed edge is F. And what we notice here is that if you look at the maximal clique two-sum components, they're either going to be the triangles, because we're looking at all the ones in G plus F, and we've also got this K4. But this K4 doesn't contain F, so it doesn't matter. And it kind of makes sense, because this K4 is just kind of hanging on an edge. That's not really, it doesn't really matter what the K4 does. So the only things that really actually are important, we can basically delete this triangle, delete this triangle, delete this K4, and then all we're looking at is this framework here. And this framework here just has this motion. So it has the single interval property, basically. So that makes sense. Yeah, I was hoping I'd have a bit longer at the end to sort of discuss this, but I'm kind of running short on time.
And actually, the forbidden minor characterization works in 2D, we know, which anyways, that non-edge you've drawn can't be retained in a K4 since it has the SIP.
Yeah, there's other ways of characterizing it as well.
Yeah,
that's true. Yeah. Yeah.
Why does somebody care about SIP?
I have no idea, but
I can give
Will might be able to answer
some answers. So you can, there's 2 papers that I'll be giving a lecture on in like 2 weeks that basically talk about the single interval property of tree decomposable linkages. And there's Dr. Seymour has papers called like How the Beast Really Moves and everything. And it uses kind of all this theory to just give you, if you give 2 realizations of such a linkage, a tree decomposable linkage, you can find a continuous motion between the 2 linkages, assuming it's flexible, 1DOF flexible. And so finding a continuous path like that is generally very hard to do. And I think current methods still, you have to give a lot of like parameters and intervals of where you think the path, or what properties you think the path has. So this gives you kind of a really fast and easy way to find a continuous motion.
Also, there is a slight generalization where instead of just getting the configuration space on one edge, if you wanted to do it on multiple, like if this thing had multiple degrees of freedom and you wanted to get the configuration space on multiple non-edges,
this would be
that's convex.
That'd be making more edges dashed, I guess.
Yeah. And that configuration space is convex. So if you want to lay out the configuration space, it becomes very easy. And we've applied this to modeling molecular assembly, where it's super useful.
So does that answer your question, Tony?
Yeah, I guess so. I have to digest this property, I think.
Yeah, it's unfortunate I couldn't have a bit more time, but yeah. Yeah, it has a lot of uses. It's tied to flattenability, as you can see, but it's not the same thing as flattenability, because I've got a K4 here and it doesn't matter, basically. It's stuff like this. Yeah, what else to say? So I had a lot of proofs on this. The characterization I gave doesn't work in 3D, even if you extend it, basically. So something like this is 3-dimensional SIP, but if we were using the extension, the natural extension, I won't go into it too much, but if we do the natural extension of the previous thing I said, this would say that it's not SIP, but it is. So yeah, it's more complicated when you get to 3D and stuff. That's something that me, Rahul, Will, and Lefty are working on at the moment. That's something we are looking into.
We had hopes for higher dimensions, but it seems extremely difficult unless you know the forbidden minors. So we're kind of lost there on 4 dimensions or higher, but 3 dimensions, you know, since we know the forbidden minors, then might be more manageable.
So yeah, to say a word on that, you want to be able to say that you want to look at basically a lot of the things boil down to special cases, and the only way to deal with the special cases is by having some idea of what they look like. So knowing what the forbidden minors are tell you what the special cases are, and then you know what you're dealing with. So if you don't know the forbidden minors, then things become very difficult, and it's very hard to say for definite what's going on in some ways. You can give some nice basic examples. Yeah.
So the partial free trees were known before Belk and Connolly's paper, so I'm guessing that's 15 years ago or so. So is it not possible that since then someone solved the partial 4 trees? Have you really searched?
I've looked and I couldn't find anything immediately. So I looked before you and Jim had a quick talk a couple of weeks ago about stuff, and I couldn't see anything then. That doesn't mean maybe I just didn't look very hard, but yeah, I couldn't see it.
Look at how the partial free trees proof went. Maybe we can do it ourselves and do partial 4 trees.
Ooh, it was quite a long paper, if I remember correctly. I would have to look into it, but it seems a lot of like you're saying that there is an issue to stop you being a partial 4 tree, so you check the possible cases of what can go wrong. And you boil it down to so many cases, they end up with like a massive class of graphs. And then they said, oh, actually, a lot of these graphs can be reduced to smaller ones and stuff like this. So they ended with a big class of forbidden minors, but they weren't minimal forbidden minors. You could get something that's smaller. And then they got the smallest possible, which is those 4. That was the rough idea.